In this set of notes, we're going to start talking about confidence intervals. And we're going to look at confidence intervals both this week and next week as well. So generally in statistics, we don't just present a point estimate as the estimate of the parameter. We want to provide some uncertainty about the estimate. And there's two issues that we need to address. First of all, we know that the value of the statistic is going to change from sample to sample. In other words, we're going to have some sampling variability. So if we're only going to use a single number from a single sample, how could we use it to estimate a parameter? Because in practice, we're only going to collect a single sample and look at the estimate from that sample. And then also, again, since we're only selecting one sample, how do we estimate the variability if, again, we're only seeing one sample? So what we do is instead of using that point estimate, that single value, we instead use an interval estimate. And an interval estimate gives us a range of plausible values for the population parameter. And so a common form of the interval is as follows, and this is probably the form of an interval that you're most familiar with. So at the center is where we have our point estimate. And you can usually think of this as your statistic when you're working with means or proportions. So for example, if we wanted a confidence interval for the population mean mu, we might place x bar at the center. And then the length of the interval on either side is what we refer to as the margin of error. Now, one thing that we are assuming here in this picture is what we have what's called a symmetric interval. In other words, the endpoints are equal distance from the center where our estimate is. You do want to be aware that confidence intervals don't have to be symmetric. You can have ones that are not, and that may depend on the sampling distribution. So just keep that in mind, but the most common ones that we see are going to be symmetric. Now that margin of error, that distance that defines the length of our confidence interval, what it does is it reflects the precision of the sample statistic as a point estimate for the parameter. And then the margin of error, how it's determined, is it looks at both the spread of the sampling distribution, so in other words, how much variability is in the sampling distribution for that particular estimator, and then we also talk about the allowable amount of error. So in other words, are we 95% confident or are we 90% confident? Now, starting out talking about confidence intervals, we're actually going to start by looking at what are called bootstrap intervals. So we need to give a little bit of an introduction to the idea of bootstrapping. And what bootstrapping does is it essentially gives us a way to look at aspects of the sampling distribution while only having information from a single sample. And what you're going to find as we talk through this is there are going to be some aspects of the sampling distribution that a bootstrap distribution does a good job at capturing. And there's going to be some aspects of the sampling distribution that it does not. So we're going to start out here with just a motivating example. So data was obtained of a survey of 395 students in the, there's been a, I'll fix these in your notes. I'm not sure what happened there. Pretty sure that was just a copy and paste error there. But we have data from a survey of 395 students from math and Portuguese language secondary courses in a secondary school. This contains a lot of interesting social, gender, and study information about the students, and you can find more information at that link that's given. Now suppose we're interested in the mean study time for all secondary school students in Portugal. And so the mean study time for the students in this sample was 2.04 hours a week, but we're interested in the mean study time for all secondary school students in Portugal. So in other words, we're interested in what's happening in the population, and we just have this information from the sample. So the sample mean is likely not the same as the population mean, so what we want to do is we want to assess the accuracy of that 2.04 as an estimate for the population mean. Now in order to do this, we do need to know about the variability of the statistic. So the first thing to notice here is since we don't have study times from the entire population, we can't actually generate the sampling distribution. Further, if we had information from everyone in the population, we would just calculate mu directly. So what we're going to do instead is to generate the sampling distribution. Notice again, we would need to take all the possible samples of size 395 from the population. We could estimate sampling distribution using the theoretical results such as the central limit theorem, and we're going to cover those methods in Module 11. What we're going to do here, though, is we're going to focus on estimating the standard deviation of the sampling distribution using a new type of distribution. And again, this is going to be called the Bootstrap Distribution. So we have a couple definitions here. A Bootstrap sample is a random sample taken with replacement, so that with replacement, that's very important, from the original sample of the sample size of the original sample. So essentially what we're going to do here is we're going to treat our sample as kind of like a pseudo population. And what we're going to do is we're going to continually resample from it, and we're going to try to recreate samples. Now, in order for this to work, one key assumption is that we are assuming that our sample that we obtained, our original sample, is a good representation of the population. If it is not, then this whole process fails. So that underlying assumption is going to hold throughout. Now, a Bootstrap statistic is the statistic computed from the Bootstrap sample, and then a Bootstrap distribution is the distribution of many Bootstrap statistics. Now, the Bootstrap distribution can be used to estimate the standard deviation and shape of the sampling distribution. And so here's how we actually go about creating that Bootstrap distribution for a random sample of size n. What we would do is we would generate all possible Bootstrap samples of size n. And so notice here there are n to the n of possible Bootstrap samples. We would calculate the Bootstrap statistic from each sample and summarize the distribution of those statistics in a plot or a table. In other words, we would look at the probability of obtaining each of those statistics. So kind of in a picture summarizing what we just saw, what we do is we start out with our original sample. So in terms of our example, remember that we had this sample of students, and in particular we had 395 of them. So our original sample is that 395 students, and then our original sample statistic was that x bar, which was equal to 2.04, and that was the average study hours for that sample of 395 students. Now, what we do to create each of the Bootstrap samples is we start with our original sample, and then with replacement, we're going to sample 395 observations. And we're going to do this for each of these Bootstrap samples. So notice each Bootstrap sample is going to have 395 observations. And then for each of these, I'm going to calculate an x bar. So I'm going to calculate the mean from those 395 observations, and that's going to be a Bootstrap statistic. And then we look at these statistics to create the Bootstrap distribution. So notice this is very similar to a sampling distribution in terms of the overall process, because when we talk about a sampling distribution, the only difference is in a sampling distribution at this stage right here, we have the population instead of the original sample. Other than that, the process is the same. So this is why we say that this original sample is acting as a pseudo population. And again, cannot stress enough, one of the fundamental things is we have to have this original sample as a good representation of our population. So a couple properties of the Bootstrap distribution. It's going to be centered at the original statistic. The variability of the Bootstrap statistics is going to be similar to the variability of the sample statistics. And again, this is as long as that original sample is a good representation of the population. The standard deviation of the sampling distribution can be estimated using the standard deviation of the Bootstrap distribution. And this is the big idea here, because our whole idea is we're trying to estimate the variability of our statistic. Bootstrap distributions give us a way to do that. So it's all about estimating that variability. So again, let's continue our example here. So to generate the Bootstrap distribution, notice we would need a lot of Bootstrap samples if we were actually going to generate all of the possible Bootstrap samples. So in practice, this is generally too many for exhaustive calculation. So instead what we do is we draw random Bootstrap samples and calculate the Bootstrap statistic for each. So in this case, I generated 100,000 Bootstrap samples. And usually, some books recommend 10,000. I've seen some do 100,000. Usually what you want to do is you want to generate a large number, increase it a little bit, and make sure there's no distinct differences between the Bootstrap distributions that were calculated. And if you're not seeing much change as you increase the number of Bootstrap samples, then you are probably fine. In other words, you're looking for that distribution to kind of stabilize as you increase those numbers. So, a couple things to notice looking at this image, first, notice this is centered at that 2.04. So it is centered at the original statistic. Now remember, we know about the sampling distribution of x bar. We know that it is normal. Well, notice here in this case, the Bootstrap distribution has a similar shape. And it ends up that the variability of this Bootstrap distribution is very similar to the variability of the sampling distribution of x bar. Now for everything that we're going to be doing for Bootstrap distributions, we're only going to be using Bootstrap distributions to estimate confidence intervals when the Bootstrap distribution is symmetric and bell-shaped. It is possible to get Bootstrap distributions that are skewed, and there's different recommendations for when that occurs. And if you go through and you look at the literature, and I'll talk about this here a little bit more, some of the methods that we use are not recommended, and the reason for that is they do not work as well when your Bootstrap distribution is skewed. So that's why for what we work with, we're going to look at ones that are symmetric and bell-shaped. Alright, I want to talk about the plug-in principle. So previously we stated the Bootstrap distribution can be used to estimate the standard deviation and shape of the sampling distribution. Here we'll discuss what the Bootstrap does, why it works, and what we cannot do with it. So in the field of statistics, we often utilize what is called the plug-in principle, and you've actually seen this before, we've just never called it this. Simply stated, it says if we don't know the value for something, we plug in an estimate for it. So if I don't know the value of the population standard deviation, I plug in the sample standard deviation. And so our goal is to estimate the sampling distribution, but in bootstrapping we don't know the population, so we're going to use the sample as an estimate. In other words, again, the sample is the pseudo population. So our goal is to estimate that sampling distribution again, and so the sampling distribution, notice, depends on the following: the underlying population, the sampling procedure, and the statistic. So the Bootstrap procedure estimates the underlying population with the sample, so the estimation actually occurs at this stage, and then it mimics the real-life sampling procedure and the calculation of the statistics. So that's why this works. But again, this really depends on whether or not that sample is a good representation of the population. So for example, if you have a population that is very, very heavily skewed, if you take a random sample from that population, your sample is most likely going to come from the portion of that distribution where most of the observations lie. You're probably not going to get many samples from that tail. You might not get any of the observations from the tail, depending on how large your sample is and how heavy the skew is. So keeping that in mind, you might be missing part of the population. So if we think of a picture here, if we have a heavily skewed distribution, what may happen is you may just be pulling your sample from this piece, and if you do that, notice that would give the false impression that your population looks like this. So for that reason, we have to be very careful when we think about whether or not our sample is a good representation of the population. All right. So let's talk a little bit more about estimating the population distribution. So we're going to let capital F and F denote the CDF and PDFs for some unknown distribution. Here I'm going to assume they're continuous. And we're going to let X1 through Xn denote a random sample. One possibility is to make an assumption about the population distribution and estimate the parameters of the distribution from the data. We could then take Bootstrap samples from the distribution with the estimated parameters. And so this is what's called Parametric Bootstrap. So for example, what this is saying is I could make the assumption that the population is normal, and then what I do is I calculate the mean and the standard deviation from my sample. Then when I go to perform my Bootstrap simulation, what I would do is instead of sampling from my original sample, I'm going to sample from a normal distribution which has mean equal to my sample, or sample mean and standard deviation equal to my sample standard deviation. So this is what we mean by Parametric Bootstrap. We're going to assume what the population distribution is. Now most of the time in bootstrapping we want to make a few assumptions as possible, and so for this reason we will often resort to using the empirical distribution, which is the distribution of the sample data. So this idea right here, if we go back up, that's what this plot, or pardon, this image was illustrating. This would be using the empirical distribution, And then this bootstrap distribution was also found using that method. All right, so we're going to talk about two different types of bootstrap intervals. There's what is called the empirical bootstrap interval, and there is the percentile interval. So suppose that theta hat is an estimator of theta. To make the confidence interval, we need to know how much the distribution of theta hat varies around theta. That is, we'd like to know the distribution of this piece right here. So notice delta is random. The reason it's random is that theta hat is random. So we could use percentiles of the distribution of delta to create confidence intervals. So what we would do is we would look at our estimate minus the lower quantile for delta plus the upper quantile for delta. So in other words, if I looked at the distribution of delta, we would have one endpoint here and one endpoint here. So the Bootstrap Principle offers a practical approach to estimating the distribution of that difference, which is what we're interested in. Now, notice what we're going to do is it says that we can approximate the distribution by this right here, where theta hat is that bootstrap statistic. So we estimate the distribution of delta by looking at delta star, where delta star is a bootstrap statistic. So this is one way that we could go about bootstrap intervals, and again, this is called the empirical bootstrap interval. Now, we're not going to actually program this one. I just wanted you to be aware of it. We're actually going to focus on what are called the bootstrap percentile intervals. And these, when I look at introductory bootstrap material, is by far the most common that is known. There's some materials out there that say you should never use this method, so there is some debate over whether or not this method is good. But there does seem to be a consensus that as long as that bootstrap distribution is, nice and bell-shaped, that this method is fairly reliable. So we're going to construct several different types of bootstrap distributions that follow, that bell-shaped distribution. We're going to find percentile intervals. We're going to do that a lot in the next section. But just to give you an idea of how this works, if we wanted to create a 99% confidence interval, what we do is we find the bootstrap distributions. This is a bootstrap distribution. And then what we do is we find the quantiles of that distribution, and these are going to give me my lower and my upper bound for my confidence interval. And again, we're going to look at lots of these in the next note set.